Hi everyone, this is Professor H. Rahman from Agricultural and Food Engineering Department, IIT Kharagpur. I welcome you all to this NPTEL online course on traction engineering. This is lecture 35 where I will take a tutorial how to find out the optimum ballast level and what will happen when you cross this optimum ballast. That means you will over ballast or under ballast, then how it is going to affect the performance. For a 35 HP tractor working at a forward speed of 1.25 meter per second. So mainly I will try to highlight the optimum ballasting conditions based on the recommendations given by doyers. Then I will try to find out what will happen if you over ballast it and if you under ballast it. So when engine power is 35 HP, weight of that tractor is 2400 kg with a static weight distribution of 65% on the rear axle and 35% on the front axle. So this is the two-wheel drive tractor. So I have given you the transmission efficiencies if you are moving from flywheel to PTO or flywheel to axle. We need to find out how much will be the axle power if the engine power is 35 HP. So what I have done is I have taken 35 HP, converted it to kilowatts, so multiplied with 0.746, and then I multiplied with the transmission efficiency. That means I have converted the flywheel power to PTO power, and then from PTO power to axle power I multiplied with 0.96. So that way I am getting 20.80 kilowatt. Okay. So for an engine power of 35 HP, I am getting 20.8 kilowatt at the axle, and the tire specification is which is fitted to the rear axle is 13.628. This is a bias ply tire. So section width is 0.34 meter and overall diameter is 1.27 meter, and the deflection ratio you have taken as 0.2 and considering an aspect ratio of 0.75. We will verify the ballasting conditions on a medium soil where the cone index is 500 kilopascal. So as I said, the main thing is the mobility number. So we followed the mobility number developed by Brixius. So Bn is equal to CIBD by W into 1 plus 5 del by H into 1 plus divided by 1 plus 3B by D. So all the equations developed by Brixius are noted down here. Rho is the motion resistance ratio, and mu g is the gross torque ratio or the coefficient of gross traction, and the difference is difference of gross coefficient of traction and motion resistance ratio is nothing but your coefficient of traction, COT, which is denoted as mu. And tractive efficiency is nothing but the axle power by drawbar power by axle power, or in other words it is the ratio of COT by CGT. COT is the coefficient of traction divided by coefficient of gross traction into 1 minus S. S is the slip. And drawbar power maximum, if you want to calculate, then axle power has to be multiplied with tractive efficiency. And theoretical speed of operation we have taken as 1.25 meter per second. Okay. Now what is the dP actual? That means drawbar power actual. So that we have taken from the coefficient of traction side. Since there are two wheels, so I have multiplied with 2. W is the dynamic weight on the rear axle on one of the wheels, and mu is the coefficient of traction of one of the wheels. So coefficient of traction is nothing but mu is the coefficient of traction is nothing but P upon W. So P into W into mu will give you P. So, P will be equal to W into mu and Vt into 1 minus S, Vt into 1 minus S will give you the value of V actual. So, P into Va will give you drawbar power. I have multiplied with the 2, that means for 2 wheels I have multiplied with 2. So, P into Va will give you drawbar power developed by a tractor. These are the governing equations based on which I am going to discuss. Now, for optimum ballasted condition, that means I followed the Doer's recommendation, which is nothing but W upon P. W is the dynamic weight, P is the axial power, this is equal to 1.79 V. So, for a 35 HP tractor, we calculated that axial power is around 20.8 kilowatt. If I am 20.8 kilowatt. Okay. So, 20.8 kilowatt is the axial power, P axial. Now, B is the actual speed, we have taken as 1.25 meter per second. Under this condition, what should be the weight, optimum weight, so that we will extract the maximum power from the tractor. So, W from this expression, W will be equal to 1.79 upon V into P axial. So, P axial is known, V is known, so I will find out what will be the value of W, and based on that we try to plot. The blue line gives you the maximum power and this orange color line gives you the actual power which is delivered by the tractor. So, to get this blue color line, what we have to do is the tractive efficiency has to be multiplied with axial power. That is it. And tractive efficiency has to be multiplied with axial power. So, this has been plotted for different slip values starting from 0.05, that means 5% slip to up to 23% slip. So, what we observe is at one point this actual power which is transmitted by the tractor is crossing the maximum power which a tractor is able to deliver. So, that point I have indicated is occurring at a slip of 18% and the power which you are getting is 13.35 kilowatt. Okay. Now, I will show you if I reduce this weight, if I increase the weight or reduce the weight, both the conditions I am going to check now. So, weight required is 14.9 kilonewton. Now, I will increase the weight by 60%. That means, initially it was the optimum loading condition was 14.9 kilonewton. Now, I have increased by 60%. So, that becomes 23.84 kilonewton. And I carry out the same exercise. That means, I try to plot the maximum power able to be transmitted by the tractor, which is denoted by the blue line, and the actual power which is delivered, that is represented by this orange line. So, what I observe now is it is touching at a point, both the curves are meeting at a point, this point, which refers to a slip of 11% and the power, maximum power is only 10.45 kilowatt. Okay. Now, what happened? I try to decrease the weight. Instead of 14.9 kilonewton, I have decreased the weight to by 40%. Now the weight has become 5.96 kilonewton. Okay. So again I carried out the same exercise. That means blue line is for maximum power which a tractor is able to transmit, and the orange line is the power which is actually transmitted. So what we observe is there is a huge difference. Though the tractor is able to develop transmit 16 kilowatt, but we are only utilizing 6 kilowatt, 10 kilowatt is lost. And the maximum power which we are utilizing is at a slip of 25%, which is not permissible. 7 kilowatt at 25%, which is not permissible. So if you compare these three, initially we are getting in the optimum ballasting condition, we are getting somewhat 13.35 kilowatt at 18% sleep, 18% sleep. So optimum condition 13.35 kilowatt at a sleep of 18%, and in the over ballasting condition we got 10.4 kilowatt at sleep of 11%. This is over ballasted, and corresponding to this over ballasting condition, if you draw the line, it is only 10 kilowatt. Maximum power is only 10 kilowatt. Now under ballasted condition, maximum power is 16 kilowatt. 16 kilowatt, but it is only utilizing 6 kilowatt or sleep of 25%. And if you look at the optimum condition, the maximum power developed is around 14 kilowatt. This is around 14 kilowatt. So this is the difference which you are getting. If you are, this is optimally ballasted. Okay. So look at these figures now. So that itself indicates what is exactly happening. So you are closer to 14 kilowatt, the maximum power where which a tractor is able to transmit. Whereas in case of over ballasting condition, we are developing only, we are utilizing only 10.4 kilowatt. We are supposed to get 14 kilowatt, but we are not developing 14 kilowatt. There is a loss. At under ballasting conditions, we are only utilizing 6 kilowatt. We are supposed to utilize 14 kilowatt. So whether it is over ballasted, whether it is under ballasted, in both the cases there is a reduction in power which a tractor is able to transmit. So both are not suitable. So always we try to maintain a weight which is closer to the optimum ballasting condition, so that we can extract maximum power from the tractor. Otherwise there is a loss. Now let us see one more problem. What weight should be recommended for a 45 HP two-wheel drive tractor with a total weight of 2400 kg to get the maximum output from a tractor when it is operated at 4 km per hour. Assume static weight distribution as 65% on the rear axle and this is 35% on the front axle. So how do you recommend this? Total weight is given as 2400 kg, okay, and weight distribution given as 65, this is 35% on the front axle and 65% on the rear axle. Then it is to be operated at a 4 km per hour. So that is the actual speed. We need to operate the tractor at 4 km per hour. Okay. So the recommendation is, if it is a 45 HP tractor, what is the power which is available at the axle? You have to find out what is the axle power. How do you find out? You need to know the transmission losses. Okay. You need to know the transmission losses. So if I put this is the transmission losses. That means 45 HP into 0.746, that becomes your kilowatt. Then I multiply with 0.82 to 0.84, so suppose I take 0.83, so that will give you power at the PTO, and then I again multiply with 0.96, so that will give you axle power. Since we have to follow this Doer's recommendation for optimum ballasting, so dynamic weight by axle power will be equal to 1.79 by V. V is the actual speed. So that means P axle is known from here, then W has to be found out. So 1.79 by V. V is nothing but your 1.4 km per hour. So 40 by 36, 1.11 meter per second. So this into P axle. So that will be the dynamic weight which is to be given in kilonewton. Now under static condition we have got 65% of the weight. So that means 2400 into 9.81 into 0.65. So divided by 2, that will give you weight on each wheel. So suppose this is W rear 1. Now we are getting a value of W from here. So I multiplied 9.81, that will give you Newton, then I should divide by 1000, so that will give you kilonewton. Okay. Now this is the weight on the axle, dynamic weight on the axle. So I will divide by 2 to find out what is the dynamic weight required for getting the optimum ballasting. So W by 2. So now we will find out what is the difference between these two, W by 2 minus WR1. So that is the amount of weight which has to be added to either of the wheels. That means you have to add to each of the wheels, not either of the wheels. We have to add this amount of weight to the rear wheels. Then only you can get the optimum ballasting condition, and you can able to developed maximum power. The tractor can able to transmit maximum power. So the main thing is, first we have to convert the engine power to axle power, because the Doyer's recommendation is based on axle power. So that's why you have to convert the engine power to axle power. If drawbar power is given, then from drawbar power you can also convert it to axle power, taking the tractive efficiency into account. But since in this problem its engine power is given, so directly we multiply with this transmission ratios to find out what is the axle power. Then once you know the axle power, following the Doyer's recommendation, W by Px is equal to 1.79 by V. So we know at what speed we are going to move in the field. So that will decide how much should be the dynamic weight on the rear axle. Okay. Now dynamic weight on the rear axle, if you find out from this equation, because Px axle power is known, velocity forward velocity is known. So now we find out what is the total axle weight dynamic, and then divided by 2 to find out what is the total weight coming on each of the wheels. That is a requirement. Then what is coming on the actual condition, which is nothing but from the static weight distribution you can find out, since this is given in kg, so I have multiplied with 9.81 into 0.65 by 1000, so make it kilonewton, then divided by 2 to find out how much is the weight which is coming on the one of the rear wheels. So now the difference of W by 2 and the weight which is coming from here, which is denoted as WR1, so that will give you how much is the extra weight which is required, and that has to be added to the wheels of the rear axle. So I have given you how to recommend the optimum ballasting weight, so that you can extract maximum power. Then also I have discussed if you are overloading it or you are underloading it, then how it is going to affect the performance of the tractor. So this will give you a more or less an idea how to go for ballasting a two-wheel drive tractor to get the maximum output from the tractor. That's all. Thank you.